There are two ways to name alkenes. One uses what many people call common names, a single word that may or may not tell you what the structure is from the name itself. I'll give you a few examples in a minute. The other way is to use the IUPAC systematic rules for nomenclature to develop a name that tells you exactly what the structure is. I'll walk you through that and give you some examples, but first, back to the common names. The simplest alkene is often called ethylene. It's easy to see how that name comes about. Ethane is the two-carbon alkane, and this is an alkene, so they call it ethylene. The alkane with one more carbon is called propane, and so the alkene with one more carbon is called propylene. Other common names don't give you any clue about what the structure is. Here's an example, beta-farnesene. What the heck is that? It's just a name, like Susan or Dick. You have to know the structure or look it up in a book. So beta-farnesene is this exact structure with this exact arrangement of double bonds. There are some groups that you should also know. Methylene is one. And methylene is a one-carbon group that has a double bond. How is that possible? Well, it must be attached to something else. For example, there's a methylene group here in beta-farnesene. The final group is also common. It's ethylene missing a hydrogen with something else attached, and it doesn't matter what's attached. An example would be vinyl chloride. Here's the vinyl group in vinyl chloride. And finally, the allyl group is also common. It's the vinyl group with the CH2 added. And again, it doesn't matter what's attached to the CH2, but it is attached at the CH2, not one of the double bond carbons. Allyl bromide is an example. Allyl bromide is two words, as is vinyl chloride. Let's look at the IUPAC rules for nomenclature. The advantage to using this systematic approach for naming is the names tell you exactly what the structure is. The disadvantage is these names are large and cumbersome to use. It's a simple system though. Take a look at the approach for naming using this systematic rules. Step 1. You identify the highest priority functional group in the molecule. For simple alkenes that don't have any other functional groups, that's easy. In step 2, you find the longest chain that contains the highest priority functional group. Next, you'll write the alkane name of that longest chain. Then change the last part of the name to designate what the functional group is. After that, you'll locate all the substituents along the chain, name them and place their names at the front. They go in alphabetical order. After that, you need to be able to say where the functional group is and where the substituents are. So you number the chain beginning at the end that's closest to the highest priority functional group. Then you'll use the numbers of the carbons to say where the functional group is and where the substituents are. And finally, in front of everything else, you place any needed stereochemical designators, R or S, E or Z. Following these 8 rules in this exact order will get you to the right name every time. Let's take a look at a few examples. In this molecule, there's one functional group, the alkene. We need to find the longest chain that contains that functional group. I'm going to put a blue dot at each carbon. There's 6 carbons in this chain, so the alkane name is hexane, and we need to change the hexane to say what the functional group is. For alkenes, we use the ending ene. So I need to remove the A and replace it with E. Next, I need to identify substituents attached to the ring. There's an ethyl group right here. I need to number the chain, starting with the end closest to the functional group. So we'll go from right to left in this case. And now I can use those numbers to designate where the alkene double bond is and where the substituent is. The ethyl group is on the 2 carbon, and the hexene is at the 1,2 carbon. We use just the number that's lowest. This is 2-ethyl, 1-hexene. An alternative, by the way, would put the number directly in front of the E and E. Either is acceptable. Let's look at another one. This is a very similar structure. I've just moved over the double bond. We need to find the longest chain that contains the functional group. I'm putting dots at each carbon of this longest chain. So this compound is a heptene because we have 7 carbons in the chain. Heptane is a 7-carbon chain. Heptene tells us it's an alkene. We need to identify any substituents. There's a methyl group. We need to number the chain so we can say where the methyl group is and where the double bond is. If we start at the end on the right, the double bond is on the third carbon. If we start at the end on the left, the double bond is on the fourth carbon. We'll start here on the right. This is 3-methyl, 3-heptene. We're not quite done because this alkene has stereochemistry. We need to designate the stereochemistry as either E or Z. To do that, we need to look at each carbon of the double bond separately and find the higher priority substituent. The carbon on the left, which I just drew in as tan, has two substituents, a hydrogen and a propyl group. What we need to do is look at the atoms attached directly to the carbon, not the whole group. In this case, the carbon has a hydrogen attached and a carbon is attached. This is clearly a higher priority. This is clearly a higher priority because the carbon weighs more. Now we need to look at the other carbon. In this case, the carbon has two carbons attached to it. They're identical, so we need to proceed down the line. The highest priority substituent attached to the lower carbon is a hydrogen, but the higher priority substituent up above is a carbon. Carbon is heavier than hydrogen, so the upper substituent has a higher priority. Now we notice the higher priority circle groups for each carbon are on the same side. So this is Z, and we'll build that into the name. Z, 3-methyl, 3-heptene. Let's do another one. Step 1 is to find the highest priority functional group. Well, there are two alkene functional groups in this molecule. We will name this compound as a diene. Step 2 is to find the longest chain that contains both functional groups. Let me put dots in for the carbons. There are 6 of them, so this is a hexane, and we need to change the name to indicate the functional groups. This is a diene, so it's a hexadiene. Notice in this case we kept the A from hexane to indicate 6 carbons. Hexadiene, 2 alkenes. Now we need to locate any substituents that are attached to the chain. We have a chlorine, we have a methyl, we have an ethyl. We need to name these guys in front, putting them in alphabetical order. Now we number the chain, starting from the end that's closest to the functional group, or in this case, one of the functional groups. And we'll use those numbers to say where the substituents of functional groups are. It's a 5-chloro, 2-ethyl, 4-methyl, 1,3-hexadiene. And we're almost done, but we still have to designate the stereochemistry, both of the double bond and the stereogenic center that we see here. Let's take a careful look at that compound. Notice that one of the double bonds, the one I'm putting H's on, doesn't have E or Z isomers, but the other one does. We'll look at each carbon to identify the higher priority substituent. The left-hand carbon that I just put in tan has a hydrogen substituent compared to a carbon substituent. The carbon is higher priority. The right-hand carbon that I put in blue has 2 carbon substituents, carbon and carbon. So we need to go further. On the lower carbon, there's a chlorine. On the upper carbon, there are only hydrogens. The lower substituent is higher priority. When we look at the location of those substituents, one is on one side of the double bond and the other is on the other side of the double bond. This is E. Now we need to assign absolute configuration to the stereogenic center. The stereogenic center has 4 different things attached. A chlorine, which is highest priority because it's the heaviest, and a hydrogen, which is lowest priority because it's the lightest. The other 2 substituents are both carbon, but one has only hydrogens attached to it, and the other has another carbon attached to it. So it's higher priority. We'll call it 2, and this is 3. Now we need to have the lowest priority group oriented away from us. It is. And then go round in the circle from 1 to 2 to 3. Going around the carbon, we find ourselves going clockwise. This is R. So the full name of this molecule is RE 5-chloro-2-ethyl-4-methyl 1,3-hexadiene. Pretty cumbersome, but it tells you exactly what the structure is. Finally, let's look at a cyclic alkene. To name a cycloalkene, Start with the cycloalkane name that's appropriate for the ring size. For example, this has a 5-carbon ring, so it would be cyclopentane. Because there's a single double bond, change that A in the pentane to E, pentene. Then identify and name the substituents. This cyclopentene has 2 methyl groups, so it's a dimethylcyclopentene. Now we need to number the ring so we can identify where the substituents are. You always number the ring with the alkene carbons being carbons 1 and 2. There are 2 ways to do this. We could number this way, 1, 2, 3, 4, and 5. Or we could go the other way around the ring. Remember, the carbons are always 1 and 2 for the alkene. So we'll start here, 1, 2, 3, 4, and 5. We'll use the direction that gets us to the substituents with the lowest number. So in this case, we'll go clockwise, 1, 2, 3. This is 3,3-dimethylcyclopentene. We don't have to designate the stereochemistry of the alkene, because for rings this size, it can only be cis or Z in formal nomenclature. And we don't use a number to say where the alkene double bond is, because it's always the 1 and 2 carbons. So, in summary, if you systematically follow these 8 rules for naming organic compounds, you can name all organic compounds, simple and complex, unambiguously.